everybody. I said I wasn't going to do this, but I changed my mind. I'm going to go over this year's paper 1. All right, so number 1 says, what happens when ice melts? All right, so we're increasing energy. So number 1 is correct. Adding energy overcomes hydrogen bonds. That's not it. So when it melts, the water molecules are still hydrogen bonded together. You only fully break the hydrogen bond when evaporation occurs or boiling. So we've actually, yeah, I don't know. I'm not going to explain that more. Molecules gain sufficient energy to move from fixed positions. Yes, indeed. Making the answer 1 and 3. Because remember, in ice, the molecules all align in a hexagonal arrangement. Yes. Hexagonal arrangement, and they stay locked in this position while frozen. This actually explains why water is less dense as a solid, because in the liquid, all these water molecules are jammed closer together. Also why we're not overcoming the hydrogen bonds. But when you heat them up, they vibrate faster and it can split apart. All right, so number 2 says, what is the molecular formula of the compound that has empirical formula CH2 and the following mass spec? So remember, the highest numbered peak in the mass spec gives us the molar mass of the compound. So if we know the mass of the empirical formula, carbon is 12, there's 2 hydrogens and each one is 1, that means our empirical formula has a mass of 14. Let me get let's see if I can get a little more focus. That's better. So when we take, if this is the mass of my compound, 70 or 71, and that's the mass of the empirical, 70 is about 5 times bigger than 14. That means we would have 5 carbons and 10 hydrogens, making D the answer. Another thing you could do is just add up the molar mass of each, because it has to add up to 70. So each carbon is 12. 5 carbons then is 60. Each hydrogen is 1. Since there's 10 of them, let's see, plus 10 here. That gives us a total mass of 70. Either way, you end up at D. I'm going to try to keep my explanations kind of a little bit more brief, since most of the kids that are going to be watching this have already taken this test. And, you know, maybe you want to forget the chemistry. Plus, anyways. So which species are present after 15 cubic centimeters of buta-1,3-diene has reacted with 18 sorry, hold on. I'm going to pause it and fix my pen situation. All right, I'll use this little blue pen here because it's still easy to see and it doesn't bleed through quite as bad. All right, so basically this is just a limiting reactant problem. How I like to do these, I like to put the volumes over the top of each thing. So 15 liters of that, 18 liters of that. Now, whichever one produces a smaller amount of the product will be the limiting reactant. So because we have a 1-to-1 molar ratio, 15 liters of that will make 15 liters of this. Now here we have a 2-to-1 ratio, so 18 liters of that will actually produce 9 liters of that. So this is the amount of butane that will form, so we can eliminate C and D. And now we know how much product formed. Again, it's 1-to-1, so if we made 9 liters of this, we consumed 9 liters of that. If we started with 15, we'll have 6 remaining. So B is our answer. Which electron transition corresponds to the red line? So one thing you have to remember, the colored lines are produced when electrons go from higher energy levels down to lower. So automatically choice C can be eliminated because the arrow is showing the electron going up. Now for D, we can also eliminate that because one of the things you need to know is that if the electron travels down and lands at n equals 1, then the radiation released will be in the ultraviolet range of the spectrum. So it's either A or B. Well, red is the lowest color light, which would correspond to the smallest change in energy, so A. B would probably produce, green, blue, or violet light. Since we don't know what element it is, we can't predict. Which of the following can be used to determine group? Remember, groups are the columns, right? So successive ionization energies, indeed. Electron configuration, yes, indeed. The number of occupied energy levels, no. That is what the period number tells us. So 1 and 2 only. Which element is an actinoid? So here are alkali metals, alkaline earth, halogens, noble gases. Ooh, here we have La. See that little plus sign? All of them go here. There we have Ac, actinium. They'll go all here. So the lanthanides and actinides. So the answer is Pa, protactinium. Which oxide produces an aqueous solution with the highest pH? So this is our period 3 oxide compound trends. The metals make basic compounds, and the non-metals make acidic compounds, or at least the oxide compounds. All right, so here we have carbon dioxide, nitrogen dioxide, and tetraphosphorus dicoxide, all non-metallic oxides. The only metallic oxide is sodium oxide. I gotta be honest, I thought they would have made that a little bit more challenging by throwing something on there like magnesium oxide or something like that, but hopefully everybody got that one because they didn't make it hard. Number 8 says, what is the oxidation state of cobalt in this complex? So first thing we have to look at is the overall charge. So the overall charge here is -1. That means all of the charges within the complex will add up to -1. Since we have 4 chloride ions, that gives me a total anion or negative charge of -4. Ammonia is a neutral ligand, so it doesn't contribute. The charge that would add to -4 to give us -1 is +3. Number 9 says, which type of substance has the following properties? High melting point. Okay, well, high melting point would either be an ionic compound or a network solid or a giant covalent like diamond or quartz. A non-conductor as a liquid. Well, that rules out ionic because ionic compounds have high melting points. Now, metals, you could say, I wouldn't say metallic because metals will always be conductors. So then we just got simple molecular or giant molecular. Well, because it doesn't dissolve in polar solvents, it would have to be giant molecular. Things like quartz and things. So where the bonds are where all the atoms are bonded to the max. So it's really hard to break apart that lattice, especially at the interior. Which species have resonance? Alkenes never have resonance because you cannot move the pi electrons around without rearranging the atoms. Ozone and nitrate are 2 examples that do. Classic examples. I tell my kids, if they're going to ask you which species has resonance, it's usually ozone, carbonate, nitrate, or ionic compound that has carbonate or nitrate in it. Which combination best describes the nitrite ion, NO2? Best thing you can do here is actually draw it. So we got 5 valence electrons in the nitrogen, 12 total for the 2 oxygens, plus 1 for the additional charge. That means we have 18 total electrons. I put the nitrogen in the middle and connected the 2 oxygen. I've done 2, 4 electrons so far, going up all the way to 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Now, the nitrite ion will also have resonance because those electrons go into the double bond, but the bond can move. There are 1, 2, 3 electron domains. So A and D are out. The shape in both is bent indeed, but because we have 3 domains, it's a trigonal planar electron domain geometry, which means the bond angle will be 117. What is the molecular geometry of BRF5? Again, we just got to draw it. We got 42 total electrons because we got 6 halogens there. So I'm going to put the bromine in the middle, just like we did before, and connect to the 5 fluorines with single bonds. So again, we're going up to 42 electrons. I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Ooh, I got 2 more that can go on bromine. So we've got 6 total domains. Cannot be trigonal bipyramidal because that is the shape you get with 5 domains. Octahedral, well, there are 6 domains, but the molecular geometry is not octahedral. The electron domain geometry is. So now it's between square, pyramidal, or T-shape. Well, remember, a T looks like this. So if that's our central atom, it would only have 1, 2, 3 bonds. And those other electrons would be lone pairs on there. So it can't be T-shaped, so it becomes square pyramidal by default. Which gas contributes to ozone depletion? This one is just basic memory. I haven't dove in too deeply into next year's curriculum, but I think they're getting rid of this because it's just kind of rote memorization, and that's silly. All right, so how much heat in joules does a 2-gram block of copper metal at 65 Celsius lose when it's dropped into 100 cubic centimeters of water and cools to 15? So notice here it gives us the specific heat of copper and the specific heat of water. Now here we're going to be using the mass and the specific heat of copper because we're told the temperature change of the copper. We weren't given any temperature information about water, so we can't use the water for our Q equals MC delta T. So C and D are automatically out. Now here, notice our temperature change is added to 273. Well, the change in temperature is equivalent in Celsius and Kelvin, so B is out, makes A the answer. 15 says, what is the correct formula for calculating enthalpy change? If we look at A, ooh, that little F is enthalpy of formation. If it's formation, it's products minus reactants. Here is combustion. Well, combustion, we use an energy cycle. And here we have, when we do the energy cycle, we have our reactant, we have our products, we have the reactant and products of each of those. To calculate the enthalpy of combustion, we go around the cycle. So it's basically reactants minus products. That's products minus reactants. For C and D, it's bond enthalpy. Bond enthalpy is bonds broken minus bonds formed. The bonds are broken in reactants and they're formed in products, making C the correct answer here. By the way, tomorrow or within a couple days, I'm going to do the paper 2 as well. Paper 2 was not that bad this time around. You guys lucked out. Which is electron affinity. That's one of the enthalpy changes we look at in the Born-Haber cycle. So here we have oxygen gas going over to oxygen atoms. No. That is bond enthalpy or atomization enthalpy. Here is oxygen going to a oxygen cation. Well, that would be the first electron affinity, or excuse me, the first ionization energy of oxygen. Here is two oxygen atoms gaining a single electron to become an oxygen. That's not it. Electron affinity is the energy that is released when electrons are added to create an anion. So O minus plus an electron going over to O2 minus. That would actually be the second electron affinity for oxygen. Number 17 says, which change results in the greatest decrease in entropy? So let's look at our options. Solid to aqueous is an increase in entropy. 2 moles of gas to 1 mole of gas is a decrease. So that could be the right answer, but let's look at the other choices. Here we have solid and aqueous to aqueous and gas. That is an increase in entropy. And here we have 2 moles of gas going over to 4 moles of gas. Everything is an increase but B. 18 says, which methods could be used to determine the rate of this reaction? Well, we have to look at what we've got here. Before I even look at the choices, I have no ions in my reactant side, and I have 2 moles of ions on the product side. I'm also producing H+. Woo. So the pH will decrease as this reaction goes on, so we can use that. Because we're producing ions, the conductivity will change. Now, a change in mass will only occur if some of the reactants and products leave the scene. So if they evaporate or something like that. So since we got liquids, aqueous, 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 we cannot use a change in mass, so the answer is A. 19 says sodium thiosulfate reacts with excess hydrochloric acid. Since there's only 2 reactants here, if the HCl is in excess, that means the sodium thiosulfate is the limiting reactant, and changing the amount of that will change the amount of product that forms. But Changing the amount of HCl will not. So it says the dotted line represents the mass of sulfur produced. Okay. What line represents the change in mass per unit time when the concentration of the acid is doubled? Well, doubling the concentration is going to make the reaction go faster, but because we didn't change the amount of the limiting reactant, it's going to produce the same amount of product. So B shows a greater rate, but producing the same amount of product, so that's our answer. Number 20 says the reaction between NO2 and CO gives the following rate data. What's the overall order? So for carbon monoxide, I'm going to use experiments 1 and 2. As the concentration of carbon monoxide doubles, the rate does not change. It's equal. That means it's zero order with respect to CO. For nitrogen dioxide, as we double the concentration, we quadruple the rate. That makes this second order. The overall is the sum, so the reaction is second order. Which statement is correct for the components of the Arrhenius equation? Activation energy decreases as no. Activation energy only changes if you add a catalyst. Like, think about it. Here, the activation energy is up here. A relates to collisions with the correct orientation. A is the frequency factor. Yes, that is definitional. All right, so K increases as activation energy increases. You may be tempted to choose that since we're raising E to negative EA over RT. If you increase the numerator, well, then you're multiplying E by a bigger exponent, so you'd expect K to go up, but don't forget that's negative. So a greater activation energy is a greater number, it'll be greater number, but multiplied by -1, so that would actually make K decrease. And K is independent of temperature. No, because if you leave everything the same and just change the temperature, that will change the value of K. It'll make it go up. All right, so, well, if you increase temperature. All right, so the equilibrium constant for N2O4 going over to 2NO is 0.0059. What is the equilibrium constant if we, well, it looks like we flipped it and doubled it. All right, so flipping will give us the inverse of K, and doubling the coefficients squares K, so the answer will be B. 23 says the value of K, the equilibrium between H2 and I2 is 51. If it's greater than 1, that means the forward reaction is favored. So that means the products are favored. So C and D are out, and if the forward reaction is favored, that means it's spontaneous, so delta G would be negative. 24 says, which species form a conjugate acid-base pair? Remember, a conjugate acid-base pair only differ by a single proton, so just an H. H3O plus, hydronium and water? Yes, indeed. All three of these other options differ by much more than just a single proton. Which method can be used to distinguish between HCl, a strong acid, and methanoic acid, a weak acid, of equal concentrations? Well, remember, if they're equal concentrations, right, that means they're going to produce the same amount of stuff. So measuring the volume, no, the volume would be the same. Measuring the mass loss, well, no, the total mass loss would be the same. It would happen faster with the strong acid, but you'd still get the same amount at the end. Measuring the conductivity, oh, yes, indeed, because the strong acid will always be more conductive because it's fully neutralized, or fully dissociated, excuse me. There'll be more ions, or a higher concentration of ions in solution, so more conductivity. Measuring the volume of gas produced, again, no. All right, so 26, at 298 Kelvin, the pKa of ethanoic acid is 4.76, and the pKa of chloroethanoic acid is 2.87. Which statement is correct? So the lower the pKa, the stronger the acid, which means chloroethanoic acid is a stronger acid. So A is incorrect. The higher Ka is, the stronger the acid. So B is incorrect. The pH of ethanoic acid is lower. Well, the stronger acid will have the lower pH. So no, the ethanoate ion is a stronger base. Yes, because the weaker the acid, the stronger its conjugate base is. Which combination would produce a buffer? So we've got the same weak acid and strong base here. So we want to pick the one that shows only partial neutralization of the weak acid. So here we have 25 and 50. More base means full neutralization. Here's 50 and 25 times 2, that's equal moles, so exactly equal neutralization. 25 and 25, again, equal. 50 of the acid, 25 of the base would partially neutralize, so D. I gotta be honest, this is not all that bad a paper one either. In which pair of species does bromine have the same oxidation state? All right, so here it would be +7 because you get 8 units of negative charge from the 4 oxygens, and we have to add the charge of bromine to get -1, so it's +7. Here we have 6 units of negative from the oxygen, so here bromine would be +5, so new. Here bromine's -1. Here it's actually +1. Remember, if you're unsure of which element will take its ionic charge, whichever one has a greater electronegativity will. So oxygen here will be -2, making bromine +1. So not B. Here it's -4 and +1. Right, so the bromine here would be +3, and here it's -1. That makes D. We already know that bromine's +1 here. Excuse me, oxygen will be -2, so bromine would have to be +1 to make the ion be -1. Hypobromite. All right, so which statement is correct for a voltaic? Reduction occurs at the negative. No. In a voltaic cell, the anode is the negative, and oxidation always occurs at the anode. Electrical is converted to chemical. No, it's opposite. This is an both of these are descriptions of electrolytic cells. The anode is positive. No. Reduction occurs at the cathode. Red cat. Yes, indeed. What are the major products of the electrolysis of dilute aqueous magnesium chloride? If it's dilute, we're just going to reduce the hydrogen in water and oxidize the oxygen in water. So we're going to make hydrogen gas and oxygen gas. You would make hydrogen and chlorine if it was concentrated, and you will never make the magnesium because it's easier to reduce water or hydrogen than it is magnesium. Magnesium is higher in the activity series, blah, blah, blah. Which compounds belong in the same homologous series? So to be in the same homologous series, they have to be in the same compound class and only differ by the number of methylene groups, CH2 groups. So here we have alkane, alkene, so no. Here we have alkene, so that's looking good, but let's look at the other choices. I just don't like how they have the 2 methyl groups here on that carbon. It just seems weird to me. And also, like, if that is just one, oh, that's the double bonded carbon, but that carbon is double bonded. How does that have an H and 2? Whatever. Here we have alcohol, aldehyde, carboxylic acid. Here we have aldehyde, ketone, aldehyde. So the answer is B. Yeah. All right. What's the name of this compound? So they've drawn it in an obnoxious way, but we're always going to call the carbon that's number 1 closest to our halide substituent. So this carbon is carbon 1. So the longest continuous chain would be here. That's 1, 2, 3, 4, 5 carbons. So it's going to be pentane of some kind. Since that's carbon 1, it'll be 1 chloro. So we can get rid of this bad boy. All right. And if this is the chain, this methyl group is a methyl substituent on carbon 2. So it'd be 1 chloro, 2 methyl propane, pentane, excuse me. All right, 34 says, what is the organic product when this carboxylic acid and this alcohol, which is, propane-2-ol, are heated together with concentrated sulfuric acid? So not too difficult to figure out. What happens is this H and that OH form water, and then these two things bond. So that carbon right there is going to bond there. That carbon has an H and 2 methyl groups on it. I'm going to draw this one out later. This one, because it doesn't make sense to me. Anywho, the one that looks like that is B. For 35, which reaction would be the fastest? So remember, Sn1 is always faster than Sn2. I can actually look at the camera. Sn1 is faster than Sn2, and the better your leaving group is, the faster the reaction is. So for the halogens, iodine is the best leaving group because it's got the weakest bond to carbon. And then fluorine would be the worst leaving group because it's got the strongest bond to carbon. All right, so the tertiary halogenoalkanes, do the SN1 and primary and or secondary. Do a little bit of SN1, a little bit of SN2. It depends on the solvent type, but SN1 will always be the fastest. So here we have 2 tertiary halogenoalkanes. Here we have 2 secondary, but the tertiary will always be faster than the secondary. And iodine is a better leaving group than bromine, so A is our correct answer. 36 says, why are SN1 reactions best conducted using protic solvents? Remember, the first step in SN1 is whatever the leaving group is. I'll just say BBB. The leaving group leaving is the first step. Well, it would be like this. Right? So we don't want our nucleophile to attack right away. So the nucleophile should be surrounded by solvent. So the carbocation is not we don't solvate the carbocation, we solvate the nucleophile. The nucleophile readily forms a transition state. No, because we're trying to prevent the transition state by solvating it. Transition state happens in SN2. The carbocation is stabilized by solvent. No, it's stabilized by whether it's primary, secondary, or tertiary. Markovnikov's rule. Finally, the nucleophile is solvated. Yep, that's exactly what we want to do. So D. Which structure is an E isomer? So if it's an E isomer, E means that our high priority substituent, or yes, whatever, our high priority substituents are on opposite sides of the double bond. We determine priority from atomic number. The higher the atomic number, the higher the priority. So out of all these 4 groups here, first of all, we got the methyl groups, but bromine will be the highest priority, followed by chlorine. And then these 2 are equal. I got both high priority on the same side. That's a Z isomer. Same thing here. Priority of bromine and chlorine is the highest. High priority on the same side means no. Here we just have the 4 halogens, right? So iodine is the biggest, followed by bromine, then chlorine, then fluorine. Ooh, high priority on opposite sides. That makes C. And again, those 2 would be the high priority in D. All right, so 38 says a 50 cubic centimeter sample of sodium hydroxide was weighed, and you got, ooh, nice balance, 53.894 grams. This must have been in the college chemistry lab. What is the density of the solution? Look at those answers. They're all the same. This is significant figures. We have 3 significant figures in the volume, 5 in the mass. So we round when we do the math to the lowest number. So I got to choose the answer that has 3 significant figures, choice A. Oh, wrapping it right up. Which region of the electromagnetic spectrum is used in HNMR spectroscopy? Again, that is just memorization, I guess. Radio waves. X-rays is used in X-ray crystallography and in mass spec. Ultraviolet, I don't know that, I'm sure we use it for some kind of spectra, but not the one we talk about. And infrared is used for the infrared spectrum. And what information do we get from the splitting pattern? The number of hydrogens in a particular environment, that's integration trace. Number of hydrogen atoms on adjacent atoms, yes indeed. Number of different environments, that is just the number of peaks in the spectrum. And the ratio of hydrogens in each environment, that is also the integration trace, so the answer is B. Pretty sure I got all these right. We'll find out in like November, December when we get it released. Anyways, I hope everyone did well. I hope you can use this your future chemical endeavors and have a lovely summer.